Thank you so much for having me today. So first off, I just wanted to talk very briefly about why methane is so important for my research. So if we look at methane on Earth, about 90% of Earth's methane is generated or has biological origin processes. And so I would argue that the presence of methane in any terrestrial atmosphere warrants careful and thorough characterization. And so if we look at methane on Mars, methane was first discovered a little over a decade ago via both ground-based measurements and orbital measurements. And both of the results sort of show that methane is varying over very large spatial regions and varying seasonally over time. But this discovery was very controversial because theoretical and model predictions showed something very different. So through theoretical prediction, the main mechanism for destruction process in the Martian atmosphere and the upper Martian atmosphere is through photolysis. So sunlight comes in, dissociates the methane into CH3 and H, and that gives you a methane lifetime of around 300 years. So theoretical model predictions were sort of showing that methane should be well-mixed species in the atmosphere and shouldn't really be varying over spatial or seasonal timescales. But that's not all. Because the methane lifetime is so short compared to the age of the planet, this also indicated that there must be some present-day source of methane. And that prompted scientists to ask the question, well, if methane is being produced today, where is it coming from? And there are several hypotheses in the literature that go over potential sources for methane, like volcanism, serpentinization, a subsurface process, exogenous sources like meteorite impacts, and cometary and dust impacts, and of course, one of the favorites, biology. And so, fast forward to 2012, when Curiosity was first launched. Since its landing on Mars, it's actually been taking methane measurements through the TLS-SAM instrument. And so, on this plot, basically what we have on the x-axis is time. LS is just a way to denote the Martian seasons. And then on the y-axis, we have the methane concentration. And so over time, Curiosity has been taking methane measurements at the surface at Gale Crater. And what my group was really interested in is the highest methane concentration that was reported by Curiosity. So basically, methane sort of rapidly increases to the highest methane concentration. And then 47 sols later, they see the methane right back down almost at zero concentration, which is sort of like varying at a background level of 0.7 parts per billion per volume. And so our group wanted to see if we could reconcile and recreate this behavior of buildup and then rapid decrease with our 1D photochemical model, Atmos. And it was actually mentioned in the talk in the previous section by Andrew, where we have a 1D photochemical model that is climate and has photochemistry. His was using the coupled model, and mine is solely using the photochemistry side. And if you want to know more about Atmos, you can see the poster by our session chair, Mahmouda, who's going to be in the first poster session today. But basically what happens in the model, we start at a starting point concentration, which will henceforth be on the CH4 background. That's where we're going to start. And then we know what the highest methane measurement was. And in the model, what we want to try to do is we want to try to start from the background concentration, build up the methane concentration to the highest observed measurement using the atmospheric processes and photochemistry that we know about Mars, and then start at the highest methane measurement, run the model again, and see if we can break down the methane to background concentrations in timescales consistent with the Curiosity rover. And we also similarly wanted to try this with the lowest methane measurement, where we start at the lowest, we build it up to the background concentration, and then we start at the background and break it back to the lowest methane concentration. But before we can do that, we need to know what fluxes we need to use in order to sustain these concentrations at long time scales. And so on the x-axis here, we have flux, which is basically just the rate at which the species is being released into the atmosphere. And the y-axis, we have the concentration. And these are all the fluxes that I calculated that would produce particular methane concentrations. So any flux above the black line could produce the background concentration. Fluxes above the purple line are the lowest measurement. And then this particular flux above the red line can sustain the highest methane measurement at long, steady state time scales. So then when we were trying to do this calculation, what we wanted to do was we wanted to use time-dependent calculations. Basically, stop the model at timescales consistent with the Curiosity rover to see what would happen and see how the methane concentration would change. And what we found was that if we start at the background concentration and we run the model with that flux that I showed you previously, we can build up the methane to the highest methane concentration within the timescales that are consistent with the Curiosity rover. But if we start at the highest concentration and we try to break down the methane on those same timescales, we find the concentration sort of levels off and peters off and doesn't really reach the background. For the lowest methane concentrations, we did this experiment again, build it up, and we can find that we build it up to the background concentration well within those observational timescales, and then we find that we can depict that destruction process as well. But because our results were not necessarily what we wanted in terms of the destruction timescales for that methane, we wanted to see if we could incorporate oxidant fluxes to help aid in the process of destruction and see if we could break down the methane in timescales consistent with what the rover was actually seeing. And so just to show you again, without the oxidant flux, we got down to that 1.09 threshold in about 27 Martian days. But with the addition of an oxidant flux, we found that in the timescales, we still couldn't get below that 1.09 threshold, and the oxidant flux actually didn't really accelerate the process too much. And so this led us to see, well, if we use steady state calculations, which is basically increasing the model time and letting the model go all the way to equilibrium timescales on the order of the age of the universe, we wanted to see, A, can we break down the methane to that background concentration? And if we can, how long does it take? And does the presence of an oxidant accelerate the process? And so here are the results from those studies here, where we have time now in Martian years instead of days. And then we have the methane concentration on the y-axis. And so with the OCLO flux off, with the oxidant flux off, we can see that we actually do reach and go below the background concentrations. And then with the presence of an oxidant, if we zoom into this portion here, we actually see that the addition of the oxidant accelerates the process significantly. So we're talking hundreds of Martian years to get down to the background concentration without the oxidant flux. But once we incorporate the oxidant flux, we're getting down to the background concentration in about 10 Martian years. But that's still inconsistent with the rover observations, since it wasn't years, it was 47 days. But we wanted to see if our model results were consistent with others in the literature. And so we looked to a paper, Sugar et al. 2012, that talked about methane concentrations being generated through exogenous sources, basically the Martian meteorites or chondrites, and then IDPs, which are interplanetary dust particles. They showed that that can produce 2.2 to 11 parts per billion per volume in methane concentration. And so that's actually consistent with our flux calculations and our results there. But what we wanted to do following that procedure was we wanted to see, well, can we model the background fluctuations in the methane concentration over the course of the Martian year? Because in the literature, there have been theories that methane could be varying with the UV seasonal variations. So our approach was to incorporate UV measurements from another instrument on the Curiosity rover, REMS, and then interpolate those measurements so that we have something for every day in the Martian year, and then account for the effects of dust. And step 3 is arguably one of the most important parts to this, because the dust actually has a really big effect. But we actually don't have dust particle physics in our 1D photochemical model, so I'll explain a little bit about how we account for the effects of dust. So we have the ground and we have incoming sunlight. Basically what the dust does is it blocks some of that sunlight that hits the surface. And so we wanted to sort of model that behavior, decreasing the amount of sunlight, because we know there's absorption due to dust and scattering due to dust. And so we use the standard radiative transfer equation to sort of figure out what is the flux that's actually hitting the surface. So REMS actually measures tau, and we know the original flux coming in as a model input and parameter, so we can calculate the amount of sunlight that's actually hitting the surface and then account for the effects of dust in that way. So by incorporating the REMS measurements, so we have Martian days on the x-axis, and then we have the concentration and what the REMS instrument was measuring on the other y-axis, and then we have some of the SAM data here for reference. When I incorporated a flux of methane that was staying constant throughout the year, we found that the changes in the methane were being produced via changes in the REMS and the UV. So we were showing that there are seasonal variations in methane due to the UV flux, but we found that we're only really correctly predicting one of the SAM measurements, and we're sort of offshooting and over-predicting the other two. So by incorporating a second flux and doing the calculation over again, keeping that methane flux constant, we're seeing that we can basically predict correctly the SAM measurements, but on an individual basis, and it takes a range of fluxes in order to characterize this behavior. And so just to summarize, basically for the steady state runs, we are determining the fluxes needed in order to sustain the methane concentrations, and our model fluxes and calculations are consistent with papers in the literature like Sugar et al. 2012. And for the time-dependent calculations, we're basically showing that it's easy to build up the methane in timescales consistent with the Curiosity rover, but much harder to break them down on those same observational timescales. And this is true even with the addition of oxidant fluxes. And then we found if we use the steady state runs, then we find that we can get down to the background concentration, and the process is much faster, and the destruction process is much faster with the incorporation of the oxidant. And then for the steady state calculations for the Martian year, we find that we can depict variations in the background methane concentration, and the time-dependent effects were ignored for this, but we can explain any of the individual methane measurements as independent concentrations when we use the steady state calculations. And so with that, I'll open it up to questions. Thank you very much.
Thank you, Amber. Any questions?
Do you have any hunch for what that unknown oxidant might be, and maybe why we haven't detected it yet?
Well, so the oxidant flux that I incorporated is not necessarily unknown. Those fluxes were calculated from an Atreya et al. 2016 paper that was looking at how can we produce perchlorate concentrations that have been seen by other landers and rover missions. And so we just used their OCLO fluxes and their calculated fluxes, incorporated them into the model to see if we can break down the methane concentration. Does that answer your question?
So, yeah, sorry, I'm just not an expert on this. So somehow the perchlorate is getting into the atmosphere and oxidizing methane in the atmosphere?
I believe they found the perchlorate concentrations in different rock samples that they were taking, and they were wondering how did the perchlorate get there and trying to figure out what fluxes would be needed in order to produce those perchlorate concentrations in the rocks.
Okay, I gotcha. Thanks.
Yep.
Any other questions?
It's a basic question. So you were talking about the seasonal variations, but is this only for 1 year that you're talking about, or is it more than 1 year?
Correct. Only 1 year that we were modeling.
Is there a possibility to just check year by year if there is variations there?
That's a good point, and we've actually been thinking about doing more of these studies with different parts of the Martian year, but the problem is that with the Curiosity data, I wanted to make sure that I was including some of the actual measurements so that we could have a comparison between what's observed versus what's predicted, but I definitely do want to see whether or not it's going to vary over longer timescales and year-to-year timescales and compare.
Any other questions? Okay, let's thank Amber again.
Thank you so much.